In this video, we will use a bottom-up introduction to show how we build the rendering server. The core component of the system is a rendering engine. The engine employs the ray tracing algorithm to generate photorealistic images. Ray tracing is a compute-intensive task and have been ported to GPU to accelerate the process. However, the branch divergence issue reduces the level of parallelism and causes resource underutilization, which makes the performance to degrades rapidly. To fully utilize all available resource on the server, we introduce an adaptive runtime system, the heterogeneous queue. The heterogeneous queue system manages all tasks and assigns them to all available devices on the server based on their computation ability. The workload between devices can be rearranged. If a device is overwhelmed, the heterogeneous queue system will divide the excessive tasks to other devices. With this design, we can fully utilize every CPU and GPU on the server automatically to achieve load balancing. Next, we are going to improve the user experience by using the light field technique. With the help of heterogeneous queue, we can increase the speed of rendering. However, render the images one by one cannot provide interactivity or fast viewpoint switching. The users can only see from a fixed viewpoint, for example, the front view of the objects, but cannot change the viewpoint dynamically without experiencing delays. Comparatively, adopting the light field rendering technique allows users to explore the scene by roaming among viewpoints. To achieve that, only the predetermined frames are required. Mobile VR and AR is the future trend. We implemented the light field display on mobile devices. The system is designed as a client-server architecture to support multiple connections. The light field rendering is handled by the servers due to its intensive resource usage. After computation, the server will transfer the compressed images to clients. Finally, static images cannot fulfill the needs for VR and AR applications. In our system, we allow certain level of interactivity. Users can interact with objects in the scene. They can move the objects to the new position, or add more objects to the scene. The change will be sent to the server. Then the modified images will be sent to clients in a short time. We also design an adaptive rendering scenario that drastically increase the performance, while keep the acceptable image quality. After the overview introduction, now we are going to discuss about the key techniques implemented at the server side. We'll talk about the problems and how to counter them by adopting those techniques. The first is the high-level task abstraction and the heterogeneous queue. In a heterogeneous computing environment with multiple CPUs and GPUs, it is common to have different versions of code to perform the same task on different devices. Conventionally, a task might be divided into many subtasks before assigning to computing devices. Each subtask is handled by a thread being forked by the master thread. Although representing the same concept, some platform-specific data structures are forced to be built for each computing devices due to different implementations. After assigning the tasks to threads being forked, the master thread must wait for them to complete the computation and join before further processing. The problem arises when the computation power differs in those devices. When a device failed to finish its task in time, all other threads need to wait for it. This results in resource underutilization. A naive way to relieve this issue is assigning the tasks in a non-uniform manner. Programmer can assign different number of subtasks based on some heuristic. However, this heuristic not works when the computation time is not predictable, especially in the case of irregular processing. The branch divergence affects the performance on most MT platforms including GPUs. Besides, the degree of branch divergence in ray tracing algorithm dramatically increases as time goes on. The performance of GPU decreases, resulted in unexpected waiting for GPU devices. To fully utilize all computation resources, we proposed the high-level task model. In this model, we do not build the platform-dependent data structure when tasks are assigned to each platform. The platform-dependent data structures are built until the corresponding computation devices are ready. This is similar to the just-in-time compilation. When a device is overloaded, the extra tasks can be reassigned to other idle devices with little overhead. Now we can freely exchange tasks between devices. We further propose a centralized task management for multiple devices, the heterogeneous queue. In the heterogeneous queue model, all tasks are placed in a queue. When a device is available, it pulls a task from the queue and executes it. There will be no idle devices until all tasks are processed. All resources are fully utilized. The effect of maximized device utilization can be observed from above figures. These figures represent the GPU timeline when rendering in traditional threading model and the heterogeneous queue model. The purple area represents GPU busy, while the white one is for GPU idle. We can see that in the heterogeneous queue model, the GPU utilization is much higher than traditional one. We can even sort the tasks based on their characteristic. Different devices pull their tasks out from different ends of the queue. Tasks that cause little branch divergence occurrence are suitable for GPUs. By sorting the tasks, GPUs will have higher chance to execute tasks that are suitable for their characteristic, and thus increase the overall performance. After a brief introduction of the task model, let's talk about another key feature in our system, the adaptive rendering. Sometimes users favor real-time response rather than image quality. For example, when they are interacting with scene objects. The heterogeneous queue model described previously can also increase the overall performance without lowering the quality. However, a more aggressive approach is necessary to achieve real-time response, and that is adaptive rendering. To reduce the latency caused by precise ray tracing, we reduce the number of samples and ray bounce. By this approach, we can dramatically increase the performance while keeping the acceptable image quality. When users are interacting with objects, we change the quality of output images so that they can preview the change immediately. When all objects are determined, the server will then switch back to high-quality mode.